Hello, everybody. Thank you very much for joining us today for our webinar on Spectrum View, a new approach to frequency domain analysis on oscilloscopes. We thank you for your participation and attendance today. If you have any feedback or other webinar topic suggestions, feel free to let us know. You can reply to my email or comment in the chat box, or you can email us later at marketing@testforce.com. I just wanted to mention before we get started that this webinar will be recorded and you'll receive an email afterwards with a copy of the recording. So you can go ahead and share it with anyone you think would be interested, or you can rewatch it at that point. If you're interested in any other webinars we'll be hosting, it's a very popular time to be doing webinars. We will have those all listed on our website. You can visit testforce.com/academy. And you can see everything right there with other information as well. If you have any questions during the webinar, you can make sure you ask them in the Q&A section in the right side of your menu bar there. And Brandon will be sure to get to all of those questions as we get to the end of the presentation. I'm happy to have Brandon from Tektronix on the line. He's going to be presenting today, including doing some demos. So I'm looking forward to this and hope that you all enjoy it. So we'll look forward to answering your questions at the end of the presentation. Now I'll pass it over to you, Brandon.
Awesome. Thank you for the great introduction there, Marla. I wanted to take a quick minute here right off the top and thank my friends over at Testforce for helping put together this webinar, getting all the logistics organized, all these people brought together, and given me the opportunity to talk about one of my favorite features. I really like to geek out on some of this cool new stuff that we're doing with our scopes over here at Tektronix. So got a quick little agenda here set up for what we're going to talk through today. So Spectrum View is a new approach to frequency domain analysis on your oscilloscopes. So we're going to go through a couple of different sections before we get to that Q&A that Marla mentioned. So first, I'm going to introduce what the next gen scopes are at Tektronix. So we've recently redone our portfolio here. I'm going to give a quick demo at that point, just to kind of dive right into frequency domain analysis, why we do frequency domain analysis and how it can be insightful in your designs or in your system debug. We'll then go into 3 or 4 more advanced demonstrations. So once we've kind of got our feet wet and understanding the intro material, dive into some of the really advanced features that are groundbreaking, first to industry, and some of the things that only our scopes can do. Then we'll go under the hood into the actual acquisition path inside the hardware of the scope to kind of pull back the layers and explain how some of this is happening and exactly how the data is being analyzed so that you can have faith in the signal integrity and the data that you're seeing on the screen. And then we'll do the Q&A session. So feel free to type comments in the chat window throughout the conversation. Feel free to wait until the end. If there's stuff that we don't get to or that is a little bit more niche to your application that I'm not familiar with, we'll get you in contact with an application engineer, and we'll really dive into the details of what it is that you need to learn more about. So my hope here today is that everybody leaves the webinar with a few new scope-based techniques for understanding the RF signal behavior going on in your systems. So with that introduction here, we're going to dive into which scopes have Spectrum View and why tech spent all this time and money developing the feature. So it took a complete rototill of our hardware and as well as the software user interface to unlock these capabilities. Our scopes, probes, and the software that drives them are made by a real world-class engineering team that I'm honored to work alongside with. We've been making scopes for over 70 years. To refresh a portfolio like we did, we had to send many of those engineers out to visit with customers like you, to join you in your labs, of course, before social distancing was the new norm, and to see exactly what it was that was tripping up new product developments, manufacturing tests, and what new measurements were creeping up on us. We spent the time listening to what the pains were for different groups of engineers, and here's a quick summary of some of the things that we've heard. So we've heard, I want my scope to be easy to use, just like my phone. I want to be able to pick it up after a couple of months of not using it, and for my scope to be intuitive again. I don't want to have to train the next person. I want them to just be able to click buttons on the screen and the scope to do exactly what they expect. I want a scope that's going to fit my needs in the future, not only for this project, but I really don't know what my boss is going to have me doing next year. I don't know what surprises are going to pop up in my next design, and I need a scope that's going to be able to handle the stuff that I'm working on 12 months out, 30 months out. I don't want to spend too much time creating new complicated setups or relearning how to use my equipment when I get back to it. Scopes are way too complicated and setups take a long time. There's so many buttons and knobs and menus hidden behind menus. I also need a single piece of equipment that does more than just measure voltages. Sometimes I need something like an arbitrary function generator. Sometimes I need to do spectrum measurements, sometimes logic or some serial bus decode. And then when I'm in the middle or at the end of my test, I have to document what my setup was so I can come back and recreate it myself later. I can have a technician recreate it later, or I can report out to management what I've found and what my findings are. So documentation and test results are critical to me. And then I also have a hard time finding or purchasing a spectrum analyzer. They're expensive, they're large, maybe I don't have one in my lab. Shouldn't my scope be able to easily do these measurements? So these are some of the top things that we heard when we kind of did a tour around the world, lots of different industries, whether that's education, military government, defense, new product developments. And so with that, we have done a complete refresh of our portfolio. Here you can see the big HD touchscreens, capacitive touchscreens on our three new scopes here. We have the 4 series MSO pictured in the middle, the 5 series MSO pictured on the right, and the 6 series MSO pictured on the left. So as you can imagine, the engineering team has been really busy designing these from scratch from the ground up. From the ground up includes this Tektronix ASIC right here. So this application-specific integrated circuit is capable of up to 25 gigasample per second sample rate, and we can fit up to 8 analog channels here in one of these boxes, or 64 digital channels. So there are all sorts of application-based software options that can be added on and purchased down the road to help make your analysis and debug easier and more conclusive than it's ever been before. One extra boring slide right here for you is just kind of the banner specs of the 4, 5, and the 6 series. So just to give you kind of a quick portfolio overlay of how these three fit next to each other and where they might fit on your bench, depending on the measurements you're making. So hertz all the way up to 8 gigahertz, 4 analog channels up to 8 analog channels, record length up to 1 gigapoints. All three of these are running on our new 12-bit A to D, so with interpolation up to 16 bits of vertical accuracy. So you really can tell the difference between very small deltas in your signals. The largest HD capacitive touchscreens on all three of these. So the 4 series has the largest HD touchscreen for its class, and the 5 and 6 as well. You can either run these off of embedded or Windows operating systems. And then, like I had just mentioned, a whole bunch of field upgradable advanced applications and optional features, things like protocol analysis, function generators, frequency response analysis, digital voltmeters, power analyzers, multi-channel spectrum analysis, compliance testing. All these things can be added down the road. So again, it's a scope that can grow with you. So with that, we're going to dive now into this multi-channel spectrum analysis. So we're going to start that off here with one quick demo. So I have my scope sitting next to me, and I am kind of doing a share screen. So I'm actually driving on the scope standing right next to my computer. So what I have here on the scope screen is a spread spectrum clock. You can kind of see it. It looks like it's jittering a little bit from left to right in its pulse widths. And I'm going to, you can see here on the right where I touch, we have this little circle pop up. So this is where I'm touching the screen. You can see I can do 2-point touches, double taps, open up some menus. So I'm going to drop a measurement on here. We're going to do a quick frequency measurement, and I'm going to open up some advanced statistics. So over here, I can now see that the smallest frequency that's been measured so far was 96.75 megahertz, and the largest was 100 megahertz. So we're going to turn on Spectrum View, which operates similar to an FFT. I'm going to show you the differences in this demo. And we're going to set our view of the spectrum to incorporate the highest magnitudes we've seen and the lowest frequencies that we've seen. We don't want to bury menus under menus, so we've made Spectrum View really easy to get to. You can see my mouse down here in the bottom left. I'm going to double tap on the channel badge. There's a Spectrum View tab, and all I need to do is turn that on. So we have now got a traditional looking spectrum analyzer view on the top half of our screen, where you can see we've got these markers bouncing around that are measuring frequencies that are above a certain amplitude. Down here in the bottom, we also have a badge where I can control the spectrum. Currently, it's turned on with a center frequency at 1 gig and a span of 500 megahertz. We've taken a measurement over here, which tells us exactly what we want to set the spectrum up at. So we want to go to, we'll pick something in the middle of that window. So 98.5 megahertz with a 10 megahertz span. So just a couple of clicks right there, we can now see the spread spectrum behavior of this clock. I'm going to drop some cursors on up here, and we're going to measure. Again, we're seeing down to 97 megahertz as the lower end of this clock behavior, up to 99. And it's fluctuating back and forth so that we can spread out the amplitude of this clock. That way we're not emitting any bad signals. Well, that's cool. We've been able to do that kind of analysis in the past with an FFT, right? So I'm going to go ahead and I'm going to add an FFT up here into the top left. So this is a fast Fourier transform of the same spread spectrum behavior. And I'm going to set this window up so that it looks very similar to the spectrum view window that we see here in the top right in yellow. So I double click on the graticule, and we're going to have our start frequency be 93.5 megahertz. And we're going to set our stop frequency to match that of our spectrum view, so 103.5 megahertz. And now I'm going to dial back the length of our acquisition until we get some time-based settings that make these two look similar. So you can see in the top left, I have an FFT. It's showing very similar analysis to what we're seeing in spectrum view, but I had to change some things down here in my time view at the bottom of my screen. So one of the drawbacks of an FFT is that the FFT is drawing the data from the time-based acquisition. And so as we change settings in our acquisition, like if we want to zoom in here and look at just a few clock cycles, the FFT isn't showing us very much information because we don't have enough cycles. If I do the opposite, and I take a really long acquisition, because of Nyquist theorem, I now don't have enough sample points to resolve exactly what's happening at different frequencies. So at its first pass, its most simple use case, Spectrum View enables you to have independent controls of your frequency domain. Up here, right, this was rock solid the whole time. No matter how I changed my settings on the bottom half of my screen for my time base, my Spectrum View was rock solid, really easy to set up. So with that, I'm going to close out of the FFT here. And for the rest of our demos, we're just going to be using Spectrum View. So I'm going to jump back over to the slides here, and we're going to talk through why spectrum measurements are needed. That's cool that your scope can do it, but why do I care for my measurements? The first reason that we want to look at signals in the RF domain is noise. So everything's creating some amount of electromagnetic noise or interference. When we may need to quantify how loud the noise is, what its magnitude is, or pinpoint exactly the physical location where it's coming from. These are kind of your standard electromagnetic interference measurements where you need to quantify, debug, and then understand how to pass compliance testing. As a design engineer, I've spent a lot of time in the compliance lab, kind of cycling through different modifications that we're trying to make, and I understand the pain that comes with failing and trying to reschedule time in the lab to get these things to pass compliance test. Any new product is going to have some kind of surprises pop up in that lab. The second big reason to analyze things in the frequency domain is that something that looks like a perfectly clean sine wave in a traditional volts per time view may actually have really interesting behavior going on behind the scenes. This is kind of your distortion, where you can see third and fifth harmonics where the signals are either continuing or you have a small signal on top of your large signal, which is hard to see in individual cycles. The third big application is new communications, RF communications. So one of the largest applications is RF testing in these wireless communication devices, whether that's Bluetooth, radar, televisions, low jack, cell phones, wireless networks. More and more companies are developing products that incorporate RF signals than ever before, meaning we're all learning something new, as we either need to make sure our product is a good neighbor, it's not emitting things, or that our receivers are receiving exactly what it was that we were trying to transmit. The fourth is general debug. Sometimes we get stuck on something and we're looking at it and staring at it in the time domain with a typical oscilloscope view, and just throwing up a spectrum view or an FFT or looking at a spectrum analyzer kind of gives a new insight, because you're looking at a completely different angle of the same problem. So when would you use a spectrum analyzer? First off, they're really easy to use. You set the center frequency that you're looking for. You set how wide you think that signal is, and you can see the presence of really low power signals next to very high power signals. A few things that make spectrum analyzers difficult in general debug is that they're large, typically, and very expensive. It might be difficult to get management to purchase one for your lab, or you need to borrow one from a neighboring department. Right now in our work from home environment, I'm positive that more oscilloscopes have traveled home with design engineers that are working on projects than spectrum analyzers. So we have, these spectrum analyzers also only have one input, meaning that it's difficult or even impossible to correlate multiple signals that you're interested in viewing. Wide capture bandwidth can be another thing that's really important when characterizing modern devices, where multiple wireless interfaces are being used, such as like WLAN, Bluetooth, or other frequency agile or frequency hopping interfaces. So you may be wanting to look at two different portions of the RF domain at the same time. And so when would you want to use a scope-based solution to analyze things in the RF domain, like an FFT? So scopes are everywhere. Your team most likely has one to be successful in its day-to-day operation. There might even be a few within reach of your desk right now, a couple sitting back at the office, maybe you've got one at home. Scopes are great at correlating what's happening between one signal and another. Many of the scopes originally came out with one channel, 2, 4, now with up to 8 analog channels. You can see more signals than ever before and correlate more interactions that are happening in different parts of your system. But there can be a lot of pain with setting up an FFT. There's a lot of math and planning involved in setting up your time-based settings to get the view of the spectrum that you want to be most meaningful. Kind of like that first demo that we showed, there's a sweet spot where you have to have all of your time domain settings optimized. You most likely have to sacrifice how your view looks in one so that you have something meaningful in the other. So why are FFTs so difficult to use? So the key acquisition settings for one domain conflict with the other. So this could be like horizontal scale, which in the time domain, it's going to determine your overall acquisition time. And in the frequency domain, it determines your minimum RBW. Sample rate in the time domain determines your timing resolution, but in the frequency domain, it determines the maximum frequency content. So you need a higher sample rate to see higher frequency content. And then the third large one is record length. So this is the number of samples that are stored into acquisition memory for a given horizontal scale and sample rate. The longer the record length is, the longer your FFT is going to take. I have a review here at the end of the slide deck to show how Spectrum View can speed up the analysis time more than 99% because we use a digital down converter so that we are only doing the number crunching on the span that we're looking at rather than the highest frequency content. What you really want is the ability to get the correct signal in both views at the same time. You want to set one and forget it while you're setting the other. So Spectrum View was given its name for just that reason. You want to set up your time-based settings and forget it, and then optimize your view of the spectrum, right? Spectrum View. We call these buckets here on the front of the scope our new flex channels. So you can see in this slide, I'm looking at the 5 series MSO, where we have 8 analog channels. And then this is just kind of a blown up view of one of them. In the middle, we have our traditional analog input. Down on the bottom, we have 8 ground pins and then 8 data pins for doing a logic probe. So you can plug in an 8-channel logic probe on any or all of these channels. Then that center BNC is where we pipe in the analog waveform, and Spectrum View can be turned on for each of our 8 channels. You have the opportunity to mix and match any kind of setup. So we can do 8 Spectrum View channels, 8 analog only channels, up to 64 digital channels, or any combination there within that. So now we've covered the most basic demonstration of an FFT and Spectrum View. We've covered the scopes that this works on, and then why we would do analysis in the RF domain. I've got a handful of more demos that we're going to do that show off some of the advanced options here. So I'm going to switch back over to my scope. So my scope should be presenting now on the screen again. And I'm going to turn on one of the really cool additional features within Spectrum View, which is called frequency versus time plot. So I have, again, in the top of my screen, we're showing the spectrum again. This is a spread spectrum clock. In the middle, I have my traditional time domain view. So I'm going to zoom in. Those are individual clock cycles. And the one that takes a little bit of thinking to kind of get your head wrapped around is this bottom third. So this is called frequency versus time. This is how the frequency of our spread spectrum clock is changing versus time. So I'm going to increase my record length here so we can get a longer view. We have a hardware-based trigger in the frequency versus time. So I'm going to try to stabilize this triangle wave here so we can talk about it. So inside of my trigger engine, just double click on this trigger badge or double tap with my finger. We can go into channel 1, and I'm going to now trigger on the frequency versus time. So you can see this line right here is my line where I'm triggering on a rising edge at that point. So what we're seeing is my spread spectrum clock is triangularly modulated, and we can add some measurements here. So I'm just going to go up to the measurement badge. I'm going to add what our maximum is, what our minimum is, and what our peak to peak looks like. So this frequency versus time, the center line is 0 hertz. So this is 0 hertz from our center frequency of 98.5. We then see that the spread spectrum clock is varying up 1.5 megahertz and down 1.5 megahertz. And the period of that spread spectrum clock is about 25.6 microseconds. So with just a couple of quick taps right here, we can totally understand how the spread spectrum clock is varying in time. We could look for any glitches here, right? We would be able to trigger off of any, we can go to a normal mode here in the trigger, and it would trigger any time that we surpass this 1.5 volt. We could trigger off of any spread spectrum behavior where the spread spectrum clock goes too low if we had any signals that were going down here, or we can just use that to stabilize our trigger. This can also be used to demodulate RF signals. So if you have something where you have a carrier frequency, you can set the center frequency here to your carrier frequency, and then you'd be able to see how your higher frequency content is operating on top of that carrier frequency. Next demo is going to be one of my all-time favorites, which is the turn-on behavior of this exact same spread spectrum clock. So let's jump back over to the scope view. I'm going to change a couple of settings here real quick. So we're going to turn off this frequency versus time. Just swipe that down. Let's go ahead and move our trigger back over to the channel 1 analog. I'm going to move my trigger point over to the left. So with one tap here, I can set that to 10%. This clock takes a little while to turn on. So let's do 40 milliseconds per division. I want kind of a long acquisition here. So it looks like I can get up to about 320, 360 milliseconds after my trigger point. And I'm going to reset up where it is that my spectrum is looking. So let's do 60 megahertz as the center and 120 megahertz as my span. So now I'm looking from 0 hertz DC up to 120 megahertz in my spectrum. In my trigger engine, I'm going to make sure that I'm on normal mode. I have this board sitting here in front of me with one passive probe hooked up to this spread spectrum clock. And I'm now going to go ahead and unplug the power. So my circuit board's sitting in front of me with no power connected to it. All of the FPGAs, the processors, the ICs, the spread spectrum clock, everything is turned off. I have a single acquisition set up on my scope. So when my scope triggers, it's going to acquire all of the data here to fill up the screen, and then we can analyze it. So I'm plugging the board back in right now. We can see down on the bottom right that the scope is triggered. And just that quickly, it calculated a whole bunch of FFTs up in the top. I'll show you just how many there are. We can see our trigger point here in orange over on the left, and then some interesting behavior, maybe around 300 milliseconds. So let's dive into that and see what exactly is going on. We've got a zoom window that I'm operating up here in the top. So I can click and I can drag this box to anywhere that I want, which is zooming in on the bottom of my screen to the analog waveform view. A little bit easier maybe if I use my mouse, a little easier to see. So what we can see here is the trigger point and how the spread spectrum clock pin was acting right before we triggered. So there's a little bit of interesting interaction there. And then I have this tiny little yellow box at the bottom. This little yellow box is something that we call spectrum time. Spectrum time, this is the window. If you were to grow this box up, this is the time window in which all of the data was acquired that populates the spectrum view window. So as I move that yellow box around, you can see that the view of the spectrum is updating. So here I'm going to turn on a couple of cursors. Let's move cursor A here, cursor B here. So we have about a 15 microsecond time span that's being used to fill this spectrum view from DC up to 120 megahertz. And I can pick where in my acquisition I want that spectrum view time to be. So you can see here, this is before the circuit board's plugged in, and we can click and drag spectrum view all the way through our 400 millisecond acquisition and see how that clock is operating. So you see that spectrum view sliver is getting smaller and smaller and smaller because we took such a long record. So I'm going to go ahead and drag that forward. We can see here that we're now at about 70 milliseconds. And we've got what looks like our largest signal at 13.3 megahertz. Its third harmonic here up at 39.8 megahertz, fifth harmonic and seventh harmonic. So we're going to go ahead and zoom through. We're at 100 milliseconds after the board was plugged in. About 200 milliseconds down here now. 230, and I'm not really seeing any change in my spectrum up until maybe 290, 295 milliseconds. So it's quite a long time for the spectrum, for the spread spectrum clock to start to come up, but let's look and see exactly how quickly and what the interaction is for when it isn't on until it's in its steady state behavior. So I'm moving forward ever so slowly here in time, and we start to see this 13.3 megahertz signal kind of, I'll explain it as like dancing up. So it's at 13. We can see here now that it's up to 21 megahertz. It's now moved up to 61 megahertz. It's up to 93 megahertz. And then it starts to do its spread spectrum behavior as it's bouncing back and forth. So we just learned that it took about 300 milliseconds to turn on completely and hit its steady state behavior. Now this is not something that you'd be able to do with an FFT, and you wouldn't be able to time correlate the spectrum, the view of the spectrum with the time domain. Also, think about how many FFTs have been calculated for each of these slivers. With the digital down conversion available within Spectrum View, the scope is able to compute all of these FFTs next to each other incredibly quickly. So that's the first demo that really shows off how the spectrum is changing as a function of time. The next demo that I want to dive into is a hardware-based trigger that we have built within Spectrum View. So you can see here in my slides, this is going to be the next demo that we show off here. So I'm going to have a 40 megahertz clock. So I need to switch my my probing up on the circuit board that I'm on. I'm going to do a default setup really quick. So my scope is back to its default. We'll hook up to a 40 megahertz pin. And I'm going to do an auto set as well so that we can let the scope figure out what the vertical and the horizontal scaling is for me. A couple of taps really quick, and we're going to have a frequency measurement up here so we can see how the clock is operating at 40 megahertz. Looks like it's pretty steady at 40 megahertz. If you remember from the first two demos, turning on Spectrum View is just a couple of taps away in the channel 1 badge down here in the bottom left. I'm in the spectrum badge down on the bottom where I'm going to set the center frequency to our continuous signal at 40 megahertz. Let's do a span of about 60 megahertz or so. So you can see here automatically these markers pop up. So we're able to see that our highest signal is at 40 megahertz with about 8.8 dBm. And again, in the bottom, I can change the view here of my clock, and we see no changes up in the spectrum because I have independent controls of my time domain settings and of my frequency domain settings. And we're now going to turn on that frequency versus time trace that we had. It's the same setting that we used to see the triangular modulation of the spread spectrum clock. So one tap here and I have a frequency versus time signal showing in the bottom. Now, it may be a little bit difficult to see with the screen sharing, but there truly is a yellow line right here, which is showing me that there's about 0 hertz of delta from our center frequency, meaning this clock is behaving really, really well, it seems like, right? Well, I'm going to change my trigger source from the analog rising edge, which we see here in the center of our screen, to a rising edge in the frequency versus time view. And because this is a hardware-based trigger, it doesn't miss any signals that are coming through. Whereas on the screen is only updating 60 times per second. This is a traditional LED LCD HD screen. I'm going to go into a normal trigger mode. So now I'm only showing samples where the trigger condition of a rising edge in our frequency versus time plot is showing up. I want to know a little bit more about how this clock is behaving because this is not at all how the design team wanted it to look. So I'm going to add a maximum and a minimum measurement here to my frequency versus time window. So when I tap on maximum, I get this nice little orange X mark that's showing me where that maximum measurement is happening. When I tap on minimum, I get the same thing, little orange measurement that's showing me where that minimum is at. And so what I'm seeing here, if we turn on infinite persistence, I'm seeing that this behavior where the clock overshoots, right? It should be at 40 megahertz here. It overshoots and it goes all the way up plus about 15 megahertz, up to 55 or so megahertz, which could be messing up all sorts of serial communications or any of the other items in my system that are depending on this clock to be steady at 40 megahertz. And then it undershoots here as it tries to get back to its 40 megahertz behavior. And it undershoots to about 4.5, 5 megahertz below its expected value. So if we go ahead and we turn off the infinite persistence and I stop this, let's see, let's do one more single acquisition here. We can actually even see in the time domain here when we zoom in, how those few cycles right here that correlate with this change in frequency, how those clock cycles look different. They have a smaller pulse width until we get back to the steady state. This is something I would have missed in the time domain if I wasn't able to trigger on and completely isolate these deviations in my clock. So that shows kind of the power of having a hardware-based RF versus time trigger. You can trigger on rising edges, falling edges, pulse width, timeout events, many of the standard signal types that we're used to as analog circuit designers. I'm going to jump back to my slides here, and I'm going to show a couple of screenshots here of other applications where Spectrum View is kind of groundbreaking. So this is a busy screen. You can see a lot of different colors and a lot of things going on. I have all 8 channels turned on. This is an MSO 58 8-channel oscilloscope. I have the analog waveforms on the right half of my screen. So C1 is channel 1, C2 is channel 2, so on and so forth, all the way down to channel 8. And we have these bursty RF chirps being sent by an 8-channel AWG. So we're sending in some arbitrary waveforms here into the scope. The left half of my screen, I have Spectrum View turned on. And so on the left half, we're showing different portions of the spectrum, depending on which signal it is that we want to look at. So here I've got a 1 gig LFM, it's 50 megahertz wide. Here I've got a 1.05 gig continuous wave. So you can see where it's just one single continuous signal. 110 gig chirp right here, a 1.15 gig LFM, which is 250 megahertz wide. And then we have an up-down chirp, 5-step, another continuous wave, and then an 80 megahertz wide LFM. What's really cool about Spectrum View, not only can I correlate these 8 with each other, and I'm showing, this is basically the work of 8 different spectrum analyzers, but I'm able to set a different center frequency, right? These were 1 gig, 1.05 gig, 1.1 gig, so different center frequencies, as well as I'm able to move spectrum time around. So this yellow rectangle, this is the same thing we were showing during the spread spectrum clock turn on, where we can click this box and drag it, and the spectrum is going to update depending on where I have that box in my time view. So I can set different spectrum times for each of the different channels, right? So at no one point did all of these bursts happen. So I needed to be able to unlock this spectrum time so that I could update my spectrum view over here on the left. So you have absolute complete control of what it is that you're showing in the time domain, what it is that you're showing in the frequency domain, and then independent controls of the 2 of those. This is a really a great application here. This picture is showing electromagnetic interference hunting. So you can see in the top, I have Spectrum View turned on for channel 2. It was a little bit confusing without these notations. The yellow does not correlate with the near field probe. So the blue channel is hooked up to the near field probe. That's channel 2. And so we're sniffing around the board, going around, and we're looking for where we're getting the signal that is causing us to fail our radiated emissions testing. So we found that when we lay it down over this chip, there's a couple of pins on the far side of this chip that are a little bit noisy. They're passing here intermittently up above the threshold for the test that we need to pass. And so I've left this near field probe laying over those pins. You can see here, right, the signal is okay, 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 and then we see some burst right here that's causing us to intermittently fail compliance testing. I took a passive probe on channel 1, and I kind of hunted around the board. So I touched it to a whole bunch of these different square pins. And for the first one, I saw a signal that was high over here. It was like an I2C clock. I had some really low frequency noise that was all the way across. And then when I touched this pin here, you see this burst of communications that correlates perfectly with our emission. So I was able to then kind of trace the circuitry back and see where I was getting leakage from this signal into the pins that were feeding into this FPGA. and be able to determine that the board layout here with this signal was causing that noise to leak in and emit and cause us to fail some of our compliance testing. I was able to correlate my analog signal on this pin with my RF signal here from the near field probe. The third and the final screenshot that I have, not a live demo, is again the RF versus time hardware trigger, looking at how an amplitude shift keying or an ASK magnitude changes over time. So here we have an ASK signal with a carrier frequency of 2.4 gig. So the center frequency here in Spectrum View is 2.4 gig, and it has about 120 millivolt RF burst. So you can see here, right, it goes plus 60, minus 60 millivolts. And it's being used to communicate ones and zeros. So how do I get a burst like this to show up and trigger off of ones and zeros? With a magnitude versus time trace turned on right here, we're able to use the hardware trigger to burst or to trigger on the rising edge here, the pulse width, or the timeout here. So what we have is now the ability to stabilize the signal with triggering capabilities on edges, pulse widths, and timeouts. Really able to demodulate this too. If there's any behavior within this pulse, we'd be able to see fluctuations in either magnitude or frequency with this additional plot here. So how in the world do we get these scopes to do this? So the Tech49, that was that ASIC chip that I showed in one of the pictures early on. So the Tech49 ASIC includes both of the following for each flex channel. After the signal conditioning, so the signal comes into our BNC on the front, gets to the analog to digital converter, and then some of the samples are decimated. And when you turn Spectrum View on, every other signal goes to the decimator or to the digital down converter, right? So sample 1 to the decimator, 2 to the DDC, 3 to the decimator, 4 to the DDC. The decimator is then throwing away the unneeded samples so that we don't fill up the memory too much. Or the digital down converter is digitally down converting so that we can do FFTs on the span of the signal rather than the highest frequency content. Having these two pieces of dedicated hardware provides independent control, like we've talked about a couple of times, for each domain. Also with the DDC, it provides incredibly faster analysis through data reduction. So how does the DDC work? So the sampled waveform is mixed with a signal at the center frequency. In an analog mixer, this is a real signal, but with a digital down converter, it's just a mathematical representation. So over here, like this, the ASK, the last image that we showed, this would be at 2.4 gigahertz is the center frequency. We use the digital down converter to convert that signal down to DC, and we do an FFT here just based on the span. So the narrower the span, the more sample points we can throw away. So the sample rate becomes a function of just how wide the signal is that we want to look at, rather than how high the highest frequency content is. The resulting I and Q data is then stored and then analyzed. So let's look at an example. Let's say that we wanted to measure phase noise, 50 kilohertz offset from a 900 megahertz carrier, and we needed 100 hertz resolution. So we'd set the RBW to 100 hertz, and that would require a 19 millisecond acquisition if using Blackman-Harris FFT window. So conventionally, you'd need your sample rate to be at least 2x that 900 megahertz carrier, thanks to Nyquist theorem. On the 5 series, we'd set it to 3 1/8 gigahertz. Record length would then be the 19 millisecond acquisition time multiplied by the sample rate, and you'd have about 60 million points. Performing an FFT on 60 million points is going to be pretty slow, no matter what your hardware is. With Spectrum View, we need to set the horizontal scale the same because we still want to look at the same window factor. Center frequency goes to 900 megahertz, span to 100 kilohertz, and RBW to 100 hertz. So that's just based on the phase noise we're expecting to see, the offset from its carrier, and the resolution that we need. The DDC takes that 900 megahertz and shifts it down to DC. And all we're going to do is the FFT on minus 50 kilohertz and plus 50 kilohertz. So our sample rate using Nyquist is now just 125 kilosamples. So we went from 3 1/8 gigasamples, or billion samples per second, down to 125,000 samples per second. Record length is 2,375 points. So we've reduced the amount of number crunching that the scope needs to be 99.996%. This is how we can then span a whole bunch of spectrums next to each other and use spectrum time to walk through individual FFTs. So that ends the part of the webinar where I'm talking about spectrum view, but I wanted to spend just 2 minutes really quick and talk about working remote. So if you own a Tektronix scope right now, eScope is something that you can do on your scope. Just plug a Ethernet cable into the back of your scope and type your IP address into any browser on your computer. That's how I was doing this demo here today. Is you can view the screen, click and control all of the different settings on your PC. So this is something that's free. It's included in all of the recent scopes that we've come out with. A lot of the 1,000, 2,000, 3,000 scopes. Give it a try and should be able to enable you over VPN to either control the scope that's sitting at the office. If you've got someone there who can hook up probes for you, you can do analysis from home. Or if you're working in an environment where it's not safe to be touching the oscilloscope while it's set up to equipment. Lastly, we have a new free software package called TechScope. So the base package is free, and this enables you to do analysis on your PC, no internet connection, no connection to a scope, pull in waveforms from all Tektronix scopes, some LaCroix, some Keysight scopes, and you can do the analysis right on your laptop. And again, this is a free base license with a 2-week advanced license trial. So right now, over on the left, the convenience and the productivity, as well as the data sharing, has been really useful to our engineering teams here at Tech during the COVID-19 pandemic, as well as syncing multiple scopes together and augmenting your scope that may not have the advanced analysis packages available on the 4, 5, and the 6 series scopes. So that kind of ends the material that I prepared here for today to talk through spectrum view and RF measurements. Wanted to open it up to any of the questions that have come through on chat, or if we're able to unmute ourselves here live, we can take some live questions as well.
Okay, awesome. Thanks, Brandon, for your time and for presenting today. It was really informative and I think interactive with the demos. So we greatly appreciate that. And thanks to everyone for joining in today. I answered a few questions that some of you had in the Q&A chat. So we are recording this session and you'll be getting a copy of that recording within a day or two. Once it gets uploaded, I will send an email out to you all. As well, feel free to start typing in any questions you have into the chat. Okay, we did just get a question that came in. So, okay, never mind, that was more of a comment. Brandon, did you see anything come in on your side that maybe I wasn't?
I haven't had any come in specifically to me.
Okay.
No, I don't have any in the Q&A box or the chat window specific to me. I hope that I did get one part of the way through towards the beginning that they weren't able to see the scope. I hope that got worked out. I hope my scope was presenting that whole time.
I was able to see it.
Okay, good.
Yeah. So someone's asking for the FFT. They're wondering if you could explain a little bit more about what you meant when you said manual versus horizontal models.
Manual versus horizontal models.
They referenced it was on slide 11 from your presentation.
Here is slide 11. Okay, so, okay, manual versus automatic. Yes, so part of what's difficult about FFTs is that you have to be incredibly intentional with these settings to make sure that you get a useful view. So you may need to take your scope out of its automatic mode, and you may need to control every attribute to get the view that you're looking for. So let's dive back over into the scope here. And I'm going to switch my pin over right now to the spread spectrum clock and redo an auto set. And we'll turn on a new FFT. And let's get that back over. So like right now, I need to go out of auto scale and I need to start to set up what my windows are. So I think we're doing 93.5 meg and 103.5 meg. So right now, the FFT isn't very useful, and I'm in my auto mode. So as I go into horizontal, let's take some more acquisition time here. And now I'm getting something that's useful. So just at that point right there, I had to already manually mess around with my horizontal settings. Now, sometimes you also need to go into the manual settings. Like let's say that that your scope was sampling at a slower sample rate. I would need to come in here and up this. So for this demo, I actually purposefully picked something that was easier to set up in an FFT, but depending on your signal, you might have to get under the hood here and mess around with your record length, your sample rate, and horizontal scale to really get something useful to show up in the FFT window. So I hope that answers the question here on the manual versus automatic. Whereas right with spectrum view, it's just double tap, turn the spectrum view on, and you set wherever you want the middle of your signal to be, so 95.5 meg, and then the span at 10. And now as I'm messing around with these horizontal settings, well, the FFT starts to fall apart here where my spectrum view is rock solid no matter what automatic settings I'm using in horizontal mode.
Brandon, we have another question. Can you automate measurements
Yes.
and do any kind of scripting?
Yeah, so we have some of the National Instruments scripting that you can do to control what commands you're sending to the scope. So you can have a programmatic interface control where you're turning on a measurement here. You can pick which channel. You can turn measurements on, as well as exporting that data out. So the LabVIEW drivers, there's tutorials and stuff online. Made it pretty easy to do that kind of work. It's all custom depending on what it is that your measurement is, but our TSC, our Technical Support Center, has a lot of experience helping out niche applications. You just give them a call or drop them a line on tech.com. There's a support number. And if you're looking for something really specific, they're more than happy to lend a hand to help get that set up. They're all application engineers that are highly technical and highly skilled at doing that.
Can you adjust the spectrum view time? And he's saying it was around 15 microseconds during one of your examples, and he's wondering if they can make it longer.
You can make it longer. That is going to be a function of sample rate. And so you could change the sample rate. Let's see if this part of the UI, I've got some extra slides here. It is a function of one of the acquisition settings, so it can be manually controlled by those settings. I don't have it right here at the tip of my fingers. Yeah, this is where the spectrum time actually is. So it's a function of the sample rate. So yes, it can be longer or shorter depending on your test setups.
Okay, perfect. And we have another question here. Someone who works for a university is saying students use memory sticks to save the data off the scopes. And since most of the scopes run on Windows, have you had any problems with viruses?
Personally, have not had any problems with viruses, and I haven't heard of any issues with customers having issues with viruses. One differentiator here that we have with these scopes compared to what we've seen out there in the industry is that you can have either Windows or non-Windows. So I'm presenting a slide right here that shows a open bay on the bottom of the scope. We're calling it the access panel. In here, you can drop a hard drive in that has a Windows OS on it, and your scope will then boot with Windows. If you pull that hard drive out, it's an embedded scope with a closed operating system inside, so not Windows. Yeah, I see your comment there. Great. That chat just came through. That definitely took a lot of effort from the engineering team. Again, one of the things that they learned from being out there. If you're in even a more compliant heavy zone, like maybe you're in a military or government application, there is an option when you purchase the scope as well. It needs to be done in the factory, but it locks down all USB ports, all hard drives, and so no customer data can ever be saved from the scope. Every time you boot that scope up, it looks like it's brand new from the factory because none of that information can travel out of secure labs. So this Windows option is available on the 5 and the 6 series. The 4 series is only embedded all the time. So one small caveat there.
All right, good to know. Okay, yeah, I might just have one more that came in. I think we have enough time for another question. Okay, is there, maybe you understand this a bit better, Brandon, but is there a procedure to declassify the unit?
Yes, I see that question that came in. There is a procedure. We do have it posted, I believe, on tech.com. But to the individual who asked that, I can send a direct link, or Marla, maybe have your help send a direct link to that. It's a little complicated, declass document. There's a couple of steps, so I think better to handle that one offline.
For sure. Yep, no problem. I have your contact info here. Yep, you're welcome. Okay, well, thanks everyone for your time. We're coming up to 3 o'clock. So just within the hour, we appreciate all of your participation. And again, a big thank you, Brandon, for your time today as well.
Absolutely, it was my pleasure. Thanks, Marla.
All right, take care, everyone. Thank you. Bye-bye.